Hi Calc2 class. In this video we are continuing with our discussion of infinite series in section 11.2, and we're moving on to this example. As you can see, you could split it up into 3 separate series or maybe 2 separate series. Whenever you get a math problem, my advice is no matter what or whatever course you're in, if there's an easy part that you can see how to do that part first, then move on to the harder part. Sometimes doing the easier part will make you realize something about the harder part. So we're going to go ahead and do the easier part first, which is this part, the geometric, because we had just talked about how to go about finding that series. And one thing we're going to do is we're going to do the rule where you distribute your summation sign across the sum. So let's take this one and distribute the summation sign across the sum. The reason you would do that is because the first one is easy for us because we recognize it as geometric, and we can do the easy one first and then worry about the hard one later. Because this is geometric and your number r, that ratio is 1/2, and an absolute value that's less than 1, the series converges. Not only that, it converges to 1/1 minus r, because that's how it works for convergent geometric series, and then I still have the other one. Okay, and since the r is 1/2, we can just put half in there, get 1/1 minus 1/2, which is the same as 1/2, so that's 2. So the easy part's done, and now we'll move on to the harder part. Since it's not geometric, we're not going to be able to do it that way. And then the only way that we've talked about in order to find the sum of a series at this point is to use the fact that the limit as you go to infinity for the nth partial sum is the sum of the series. So in other words, you have to come up with a formula for the nth partial sum, which is a difficult thing to do. And there's only 2 kinds you can do it for, at least in 11.2. That's geometric, which is what this one is, and this one is going to be one that we call telescoping, and I'll show you how that works. So this guy, if we had a formula for the nth partial series, we would just use the fact that the sum would have to be the limit as n goes to infinity of the nth partial sum. Okay, so to do that, though, we'll have to come up with a formula for the nth partial sum, which in general is a hard thing to do, but it is going to be possible to do it for this one. So the nth partial sum is what you get when you stop at n. Okay, so once I have it for the first n terms, then I'll take the limit. All right, to do that out, we're just going to start writing out terms like the first 3 and the last 3. You stick a 0 in, you're going to get a 1 minus 1/3. then stick a 1 in, you're going to get a 1/3 minus 1/5. Then the next one you're going to get a, put a 2 in, you'll get a 1/5, and so on. So that's like the first 3 terms. There'll also be a minus 1/7, but that's going to be followed by a positive 1/7. They're going to knock out. So let's now write out the last 3 terms. The last term will be 1/2n plus 1 minus 1/2n plus 3. Okay, so now, this is the k equal n term. Let's go backwards one, k equals n minus 1. So we'll just stick an n minus 1 wherever the k is. So that'll be 2 times n minus 1, which if you distribute the 2 is 2n minus 2 plus 1. That's 1/2n minus 1. Okay, and then if you stick an n minus 1 in here, you'll get the same deal. You'll get 2n minus 2. But then you're adding a 3 on, so that'll be a 2n minus 2 plus 3 will be a 2n plus 1. Okay. One that comes before that will be a k equals n minus 2, and you put an n minus 2 in here, you're going to get a minus 1/2n minus 4 when you distribute the 2 plus 3, so that's a 2n minus 1. And then there'll be terms that come before that too. But the point is, if you take a look at the pattern and what's going on, there's a negative 1/3 and a positive 1/3. There's a minus 1/5 and a positive 1/5. So if you go from the other direction, there's a 1/2n plus 1 and a minus 1/2n plus 1. And if you go on to the next one, you're going to get let's see. Oh, here we go. 1/2n minus 1 and a minus 1/2n minus 1. But the point is, as you move forward or you move backwards, there's always going to be the next guy to get wiped out by the term that comes later, except the very first and the last. Now these things will always be symmetric. So if the first were not wiped out, neither will be the last. If the first 2 were not wiped out, neither would be the last 2. If the first and the third would not be wiped out, then going from the opposite direction, from the end, the first and the third would not be wiped out. So there's a pattern there, and that helps you come up with the correct values for it. So anyway, the nth partial sum is just 1 minus 1/2n plus 3. So this one actually does have a formula you can come up with, and that means that the sum of the series is 2 plus this infinite series, but that's just the limit as n goes to infinity of the nth partial sum, because that's the definition of what a series converges to. The limit as n goes to infinity, the nth partial sum. So that's 2 plus the limit as n goes to infinity of 1 minus 1/2n plus 3. That guy's going to go to 0 because it goes to 1/infinity, so you'll just get 2 plus 1 minus 0, or 3. So the answer for the whole problem is 3. Okay, so this kind where all but a finite number of terms cancel, that's called the telescoping sum. So now we know how to go about solving both geometric and telescoping. All right. So there's geometric series in this section. There's telescoping series in this section. And now we're going to talk about a theorem that's called the nth term test for divergence. And here's a form of the theorem. This is what the theorem says. It says if, when you take the sum and the infinite series converges, if it converges, then it must be that the terms go to zero. The terms in the sum go to zero. That's true, but there's a more useful way to use that theorem. In terms of logic, the statement A implies B is equivalent to the opposite of B implying the opposite of A. So in other words, whenever A implies that B is true, then the opposite of B implies the opposite of A is true. So if that's true, then a consequence of this theorem, and that consequence is called the nth term test for divergence, is the opposite of the outcome. Okay, the opposite of the terms going to zero then the opposite of the part you suppose. Then it must be that the series is the opposite of converging, which is diverging, the opposite of what you supposed. Okay, so it only works if the terms don't go to zero. If the terms do go to zero, it doesn't tell you anything. And it's important to keep that in mind. Let's say, for example, if you took the sum from n equals 1 to infinity of n over n plus 1, that's not geometric. It's also not telescopic. I can't write out the terms and have a whole bunch of cancellation. But I could name the terms a sub n. This is infinity over infinity form if you let n go to infinities, but you could divide top and bottom by n. And then if you let n go to infinity, you get 1 over 1 plus 0, which is 1. So the sequence goes to 1. But that means the sequence doesn't go to 0. So because 1 is not 0, a sub n doesn't go to 0. And that means that this sum diverges by the nth term test of divergence. Now, if you take the limit of the nth term and it goes to 0, then you haven't learned anything. In terms of the nth term test of divergence, it doesn't conclude anything for you. Okay, that's going to finish up 11.2, and we're going to go on to the next section in the next video.